Hey guys. What's happening today is another contest that I forgot to register for apparently. So that's a thing, which I just realized. So, which is actually fine because again, I said I'm doing the thing that I don't really care about performance. So, missing the first 10 minutes is fine. If it's ever happened to you, the way it works when you forget to register is you can't submit until 10 minutes when extra registration opens. Which I don't really understand that design for, but that's how it works. But you can still read the problems and everything. Like, you can access the contest as a spectator, basically. Yeah. So this was a great morning. I slept like a rock, if a rock was on a boat in the middle of a hurricane, but we can diverge from that. What I should do is update the sub count that I forgot to do last time. And I guess we'll start. Mocha is a young girl from high school. She's learned so much interesting knowledge from her teachers. Wow, it doesn't happen often. So, binary system. You have a sequence A, you can select an arbitrary interval, and replace A... What does that say? L plus I with AL plus I and AR minus I? Okay. Minimize the maximum value in the sequence. So basically you can AND together the whole array, and that's the best you can do. If some bit is present in every single value, then it will always be there. Basically, consider like the minimum possible operation you can do. Like how much power do you have with your operations? That's weirdly shaped frame. I know exactly why that happened. It's because I make it super small when I try and size images. So basically consider like you have any array. If I choose L equals this and R equals this, then all I'm going to do is set these two elements simultaneously to their bitwise AND. So what I can do with this is I can say I'm going to AND these two together, then I'm going to AND these two together, then I'm going to AND these two together, then I'm going to AND these two together. And basically now this single element in the beginning gets bitwise ANDed with the whole array, because this element now contains the bitwise AND of this one. And so this element also contains the bitwise AND of this one and that one. And then we can do the same thing and we can AND this element with the whole array. And then we can AND this element with the whole array. And then eventually the entire array becomes the AND of the AND of all the elements. It's sort of a sketchy proof, so I'll do like a bitwise one too. Essentially, bits are independent, so let's go bit by bit. Assume like, so for some particular bit, assume like you have like a 0 in one location. Then what we can do is we can just spread that 0 out to everywhere. And we're trying to minimize the maximum element, so we should spread out to everywhere. So we AND these two together, 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 and then everything gets to 0. And so if there's a 0 at any position in the array in this bit, then we can spread it to the whole array by just selecting two elements and adding those together. So that's basically the strategy. Whenever we have any form of 0, then that bit is 0, and otherwise, when like all of the bits are 1, then the bit is forced to be 1. And this operation, if it's at least 1 0, then we get 0, and otherwise it's 1, is exactly what bitwise AND is. So really it turns out that the answer is just the bitwise AND of the whole array. But really this is what's going on underneath. We're asking if there's a single 0, and if so, we can spread that 0 out to every element. So implementation wise, this should be really easy. Say that and then I'm struggling with details. So we're just going to take the bitwise of the AND of the whole array. Should pass samples, I hope. And then, again, I can't submit until 10 minutes, so I will just leave that for now. But I don't see any reason why I'd be wrong. Alright. N squares in a row, and each of them can be painted either red or blue. One of these squares, some of them have been painted already, and the others are blank. You can decide which color to paint on each blank square. Okay, some pairs of adjacent squares may have the same color. Okay, minimize the imperfectness. Oh, we have to print the... Okay. That's kind of annoying. So for this problem, I'm guessing the main idea is that, like, independent groups of question marks are independent from each other. Well, yeah, I said they're independent. But, like, consider, like, a string like this, maybe? Like the first sample or something? But like, with a bit more. Like, this group and this group are totally independent because they cannot affect each other because there are no adjacent elements between these two groups. And the same for this group, and the same for, like, all of the groups, basically. Because they don't have any adjacent characters to each other. So really all that matters is the characters on either side of them. Yeah. I'm trying to figure out what's the easiest way to implement this. So how do we decide, like, the answer for a single group? And then the answer for the overall string will just be the answer for each group, like, summed together. So it's like, it's the best we can do in this. I don't understand why Paint does this. Sometimes it just, like, goes into erase mode for no reason. Like, you see I didn't even select that thing at all and it just got rid of it. Yeah. How do we decide a single group? If it's on the end, we just make it the opposite of whatever the adjacent color is. Because there's no color on this side, but there is a color maybe on this side. So the only restriction is that it can't be equal to this one, so we just set it to the opposite and then alternate. Like, we'd do red here, and then blue, and then red, and then blue, and then etc. Here, our goal is to make it the opposite of at least one of the colors. So, like, for example, here, if we made it the same as both of these, then that'd be dumb. So let's not do that. Instead, you can it's basically like, it's okay to just make it the opposite of one color and then go from there. Because at the end, if it's forced to be equal to the other one, then no matter what, you would have a forced equality. If you started from this end, it would similarly be equal to this one. So it doesn't really matter which end you start from. So basically, you just pick one of the ends, and then you start from there. You say it's going to be the opposite of that, then you alternate. In this case here, it would be alternating. And we do have this pair. But again, if I started from here, we would get the same, like, adjacent pair, because just, like, that's the way it works. That if you alternate one of the sides, it's going to be screwed over. You can sort of show that if you want, by, like, it's essentially like the length mod 2 is, like, bad or something. I don't know of an elegant way to prove it. It's more just like casework. But yeah. So code-wise, it seems kind of annoying. Basically, we're finding the endpoints. Okay, so I'm gonna use 2 pointers here. So if SRP is equal to question mark, so this is how the 2 pointer is going to work. If we're at a non-question mark, we're essentially going to keep a pointer pointing to the previous question mark. So in this case, the pointer is initially here. Then when we encounter a non-question mark here, then we know the range we want is inclusive of the left and exclusive of the right. So then we're going to process that range, and then we set the new endpoint. We know this isn't a question mark, so we set the new tentative endpoint to here. So this is not a question mark. The first thing we do is check if we have any question mark. So in particular, if LP is less than RP, then this range is existent. There's at least one element in this range, and so we process it. So we do something with that. Then afterwards, we're going to set the left pointer to the position after this one, because we know this one isn't a question mark. So LP is RP plus 1. Then we do one final thing here, the checks for the ending thing, because that's sort of separate. So LP is less than RP. Then we're looking for either of the endpoints. So if LP is not equal to 0, then there's something before the left, so we can alternate based on the left. Yeah. So we will set the initial string to the left of us to be S of LP minus 1. Then we iterate over the range, strictly not including RP because that's excluded. Then we set target to the opposite of itself. What are the colors? B and R? Yeah. So B. This is a ternary operator. You can read up on it in documentation or something. Basically just says if this, then this, otherwise this. It's like an if statement in a single line. So then SI is equal to targ. Else, if RP is not equal to m minus 1, that means we have a character to the right. So now we're going to use the target as RP plus 1, and then we have to go, because our reference character is to the right, here, now we have to go leftwards. So we're going to iterate down from that. And we're going to do the same thing. This should actually never happen. We should... Maybe this isn't necessary, but whatever. So there's the endpoint. This final condition we know is the ending part. So we can basically assume that we're going to go from the left because there's nothing on the right. So if LP is 0, then we know that the whole string is question marks. So we can say targ is anything. Else targ is equal to. Otherwise, we have to set it to whatever the previous position is, similar to here. I copied it instead of pasting it. How does that even happen? Okay. It took a while. I think I didn't even get rid of the. I think I overwrote the previous code, so that's kind of dumb. This should be up to n. What? Multitask on. Does it read in? It gives you the length. Actually, that's an important distinction because I forgot to declare n anyway. So BR, BR, BBR. No, we can. No, that's fine. We're forced to have one. BR, BR, BRB. Sounds good. R, B. This looks like the ultimate test. So BR, BRR, BRB, BR. 1, 5. Make sure it gets that right. Okay. I could check it, but I don't care, so I'm just gonna submit. And yet I'm still checking it. I think it's fine though. Oh yeah. Gotta do that. And then ideally make the submission. Okay, now I can frantically undo the code to get my code for A back. This is one of the drawbacks of overwriting code, because I just do everything in the same file. Sometimes it's bad, but like not always. Most of the time it doesn't really matter. But in this case it could potentially be bad. Now we wait for two different programs. Wait a long time apparently. City where Mocha lives in is called, sorry, I'm not going to try and pronounce that, because that's going to be bad. So there are n+1 villages and 2 n-1 directed roads. From village I to village I+1. Interesting. So it's sort of like find the Hamiltonian path, but like not. So visually it's going to look something like too far. So you have nodes like 1 to n. Say like n equals 4, then you have these bridges automatically, and I think they go both ways. No. Directed. No, they do not go both ways. So this is this way, and that's this way, and that's this way, and this goes up to n, and then you have this like special village n+1. And essentially, there's a village from there's a road from each village to the special village, and it goes in one of the directions. Either it goes towards the special village or it goes away, and it's described by this like binary sequence of zeros and ones. So we just need to print just the A. Okay, awesome. Nice. I guess we'll fix this one. Testing the compilation because sometimes copying gives me like issues with weird Unicode characters. But I guess we're fine there. 1, 7. Seems fine. Multitests? No. Doesn't seem like it. Let's try like not doing anything. Yeah. So it doesn't change the string even if it's bad. So this is not a question mark. If LP is less than RP, car targ is SLP minus 1. What did I mess up here? Notice if RP is not equal to n minus 1. We're looking to the left, right. For I equals RP minus 1. Yeah, this isn't really necessary, but whatever, I did it anyway. RP minus 1 is greater than or equal to LP. That includes everything. Oh, right. It should just be RP, because that's the end point. That should fix things. And if not, I will pay for it again with more penalty. But like, I'm already starting at 17 minutes, and I spent way too long on B to exaggerate how I'm... Okay, awesome. Working out indexing. But I guess that doesn't matter anyway. So what the hell? This is messy, huh? What is going on here? So div is equal to a question mark. We don't change anything. Oh. I might as well get rid of this, because this isn't necessary. Alright. Since we're changing it, then we set that. I feel like this is showing up as some sort of Google Code Jam problem or something. Maybe Kickstart. Seems like that type of thing. I don't understand this. Like, does that fine. Oh, what's happening there? Okay, so it's changing the... How did that happen? That's just a dumb mistake. Oh god. When I paste my code in, it means just death, because it will like process every line independently, and there's no way to stop it. And 1 5 question mark question mark question mark BR. What? Want to Right, okay, change that. So 1, 5, that's the input. What? What? I mean, this is a multitest issue, but how? It's overwriting the string. That's irrelevant. So this has problems. If I do it this way, it'll have problems. How, though? What the hell does that mean? What exactly is going on in my program here? Oh, that's why. Because I didn't put this here. So this is fine? So this is fine. So is there a problem with the idea? Remember, it's going to be forced to have some issue if, like, it's bad. I'm so confused about this. Why does this happen to me? These easy problems are more dangerous than you think. I could, like, try submitting again. Close that. I don't understand. I'm gonna just submit again. Like it's wrong, fine. Then the error was somewhere else, I guess. What did I change? What? Was it this? What did I change? LP is not, oh my god, why is it sending me for each tab? Jesus. LP is not equal to 0. What did I change? Now I'm so confused. Okay. What? There's some typo or something that I'm not seeing. It's frustrating. Okay, well, that's the thing. So now we gotta like do a thing. So we're back here. Let's consider like when we can leave. So either we start on N or we start here. If we start on N, then the road we take has to be to the first road. So because when we start on N, we can't visit N again. So we have to visit all of these in one go. And the only way to do that is to start on the first road. If we start anywhere else, then we have to start. No, we don't. We don't necessarily have to start here. What we do need to do is suppose we start somewhere else and then we maybe like end over here and then we go to N and then we go back here. Then we have this road from N to here. So we might as well start here and then go this way and be fine. So there's no reason to consider starting anywhere else from these two. And we know the condition for starting here. So now if we can't start here, that means this road is this way. Then we have to start here. Because there's no other way we can get to this node. Nothing points into it. So now, what can we do? And we have to find a point where we can go to N. So when can we go to N? And yeah, so that's the question. When can we go to N? And basically, so we're gonna start here, then we're gonna go to some point. Then we're going to, from that point, go to N. Then now we have these nodes left to visit, and because we can't visit N again, if we go to any other node except like the highest priority one that hasn't been visited, like the one that's the lowest index node, then we can never get back there because the edges only go this way. So from N, we have to go back to this node. And then from there, we go this way. So really all we need is an instance of an edge to N and an edge from N adjacent to each other. Or if it's on an endpoint, we can have just the edge from N, or if it's on this end, we can have just the edge to N. And basically this determines when we're going to put N in our sequence. Essentially, the structure is going to be, we're going to go from 1 to M minus, or sorry, I've been saying N this whole time, this should be M plus 1. My mistake. But essentially, we're asking when we can put N plus 1 in our sequence. Like if it's at the beginning, it'll be here. If it's like, it can be somewhere else too. But the sequence is going to be this with just an extra element stuck in somewhere. So the question is when. And that is a good question. So we're looking for this structure specifically. To N from N. What is what? So we need 0, 1. 0, 1. Yeah, it should always be possible then. Because if the beginning is 0, or if the beginning is 1, we win. If the end is 0, we win. So suppose neither of those are true, then we have a 0 here and a 1 here. So eventually we have to have a pair of 0, 1. So it's always going to be possible. Because like, suppose you consider the point where this stops being 0, then you have a 0, 1. And if it never stops being 0, then you'll get to here, and then you'll have this 0, 1 anyway. So let's just do that. So we're looking for if we've had a 1 yet. So for I equals 0, I is less than or equal to n. So we check the condition first. So if it should be before element I plus 1, like 1 or 2 or etc., like 1 indexing, then we consider the following. So if I is equal to 0, or I minus 1 is equal to 1, and I is equal to n, or ai is equal to 0, right? No. This is 0, 1. My mistake. So the first one should be 0, so I should go to that, and then this should be 1. This will handle the beginning. I'm pretty sure. If not done, cout n plus 1, done equals 1. If I is less than n, cout I plus 1. Yeah, so we're going to print the sequence 1 to n, and somewhere in that sequence we're going to print the number n plus 1. This should work fine. It should be even easier than b, I hope. Don't understand what happened with b. I guess I will look at that after the contest or something. But that's the plan. Essentially, we're just going to figure out when we can detour to n, because we have to visit that node eventually. Okay. It's a lot of pretests. Mocha and Diana. Okay. Forest is non-directed graph without cycles. Cool. So a bunch of trees, just in case that wasn't clear. Both of them have forests with nodes numbered from 1 to n, and they would like to add edges such that they're still forests. Wait, there are multiple? Oh my god. They're still forests, and they add the same edges. Huh. Cool. Okay. Constraints? Yeah, 10 to the 5th. Okay. So each edge will merge 2 trees in both of the individual forests. That is one part to note. Also, D is worth the same as E, which is interesting. So one edge has to merge 2 trees. I guess in this you can check each edge, and in the other one you can't. I guess that makes sense. In this you can check each edge, and the other one you can't. Okay, so you cannot add an edge if the 2 components are connected in either of the forests. You cannot add an edge if the 2 components are connected in either of the forests. But otherwise, it's just like taking some spanning tree, basically. Does it matter which components we merge? Well, no. Does it? I don't think it should. But maybe. For this one, I assume we can greedily do things. Is it greedy? I don't know if it's greedy. That's the thing. There's a decent chance it might not be greedy, and that would be a pain. So, does this mean anything? I mean, just like, merge just two things together. This is going to be kind of hard to visualize, but this is what it looks like, except this is happening in like the other component. So to greedy or not to greedy? Some samples don't change, no. What exactly are we doing with this? We have the same edges. Right, so how do we figure this out? If we add an edge in one graph, and it works in the other graph, then like what? Is it fine to add that edge? Is it better to have added some other edge? Suppose we have another edge that merges the same component in the first graph, but not in the second. And like, maybe we have no other way to merge those two components in the first. Essentially, I guess, suppose we enumerate all the edges, or just look at all of them. Some of them don't work, some of them do. For the ones that do, they will merge two components together, just like that. So maybe now we consider like the condensed graph. So instead of considering the individual edges, we consider solely the components they merge together. Maybe. So we compress each component into a single thing. And we get rid of identical edges, which don't really matter that much. Then now that we're rid of identical edges, what can we do now? Basically, the greedy will work if no edge is like a bad idea. But is that even true? Suppose we have 3 components in the first graph, 3 components in the second. It's like maybe there's an edge that does this. There's like an orange edge that does this. And then like a green edge that does this. And then a blue edge that will do this. Now, is this possible? If this is possible, then the green edge is a bad idea. Because the green edge will make it so we can't take any other edges. I'm staring blankly. Well, let me see. It still may be the case that the situation isn't possible. So, like, when would that be the case? It's like, this is like the original graph now. This is condensed, this is original below. So maybe we have like this and then something like this. There's 1, 2, 3, and 4. Actually, the thing is, all edges are possible. So there's also this yellow edge, or this purple edge, that will do something in here. Alright, so what do we need for this situation to happen? So in this case, we'll have node 1 here. We'll have node 2 here, and then maybe 3 and 4 like this. Is that how that works? No. Well, maybe. So orange would be 1, 2. That's fine. Green would be 1, 3. And then blue. Well, that doesn't work. What do I have to do exactly? Maybe, no, that's wrong. I think this component needs 2 nodes. Anyway, I feel like it's still not going to be possible. So this is 1, 2, 3, 4. I don't know where the extra node goes here. But like, this is orange maybe. 2, 3 is green. And then 3, 4 is blue. So 1, 3 is orange. So 1 has to be here, 3 has to be here for this to be orange. Then we need 2, 3. What did I mess up? Okay. Well, so this is 3, this is 1. And this is orange. I'm trying to just make it like look visually similar. Maybe here is 2 and 4. We can get this situation, I guess. But then like there's still the other edges is the thing. Like this isn't the only thing we can do. Like, we can add every single edge that works. So is there ever a case where an edge is a bad idea? I'm still thinking no. If we have two components that have no mutual edge, I'm feeling it's the same idea that like constructing a spanning tree is like greedy. We might as well take any edges that don't hurt. I think it's the same way here. Or is it? Like, the issue is like one mistake prevents us from having multiple edges in the future. One mistake prevent us from having multiple edges? God, my brain is not ready for this today. But that's what we're doing. What are we doing? Still can't convince myself that it's possible. The edges we can add here are this and this. These are identical in function, so that's fine. Oh, we can add edges from one, but that's the same thing. The graph we consider when we're thinking about edges is like weird. Because we can't take the union of the two graphs, because that'll have issues. Yeah, we can't take the union. I could submit the guess. But I don't want to like actually think about it. I don't want to. That's not the point of doing these. You can guess that you can greedy. But when would it ever be the case that greedy is bad? Conjecture is never. You take some edge. It can prevent one component from happening in this place. How would it prevent two edges? How is that possible? I don't understand how that would be possible. If there are two edges that could happen, and then we merge this one instead, then like it prevents one of those two edges, but it can't prevent both of them. Because those two edges, by definition, merge different components in each forest. which is true. So then if those two edges maybe result in the components of the first edge being merged together, then we instead just don't take one of those two edges. And then that should be fine. It's gotta be greedy. It's gotta be greedy. So intuitively greedy. I'm just gonna submit. Yeah, okay. It kind of makes sense. Like if you have two edges, I think like taking any edge can only remove at most one of them. So like it can only penalize you by at most one edge, which is fine because we got one edge from this anyway. I'm looking for DSU. DSU D1, D2. Is this multitest? No. I'm going to specifically not use M1 because that's hard to tell the difference. So d.init m, d2.init n. Bool. Basically, I'm just adding a flag so it returns true if it did merge something and false if it didn't. Then up to M2, we do D2. Now I consider each edge. Oh wait, okay. Whatever. D.marks I is not equal to D.marks j, and the same for D2. So essentially, there's both of them are not in the same component. And stop push back ij, d.merge ij, d2.merge ij. What was that? What's that for? They have some queue issues? And of course they're gonna do it for every tab. So that's awesome. So I should note that this is not the best contest strategy. If you have some reasonable guess and it's going to take a while to prove it, then it's probably a good idea to just submit it. So what I was doing here was not the best contest strategy. What I'm doing here is the fact that this is a screencast and I don't care about performance. But in general, if you have a guess like this and it like seems plausible and you have a lot of time, it's a reasonable idea to just submit it. And if you're wrong, you'll get a penalty, which is fine. I've already accumulated a lot of penalties, so a little more can't be that detrimental. But yeah, so this does pass. And it's okay to make a guess sometimes. Like, it's okay to do that. Sometimes it's worth the penalty that you'll have to make that attempt and like rule out some solution. Because you'll be kicking yourself really hard if you miss that really simple thing that you already thought of and you didn't think was correct, and then you never pursue it, and then, you know, it's sad. So this part's harder because the constraints are bigger. Here, we simply tried every edge, we did greedy. In n equals 10 to the 5th, of course, that's not going to work because n squared edges. So what we need to do is efficiently find edges that work in both graphs. Let's consider the node 1. Actually, how do we think about this? I'm thinking complement graphs, where we take the graph consisting of every edge but the edges that are in the forests, maybe. Then like the intersection of the complement graphs is the thing we can use. But that's like, how do we find, like that can also be n squared. Suppose we have no edges, then the complement graph is everything. So we can't really like iterate over the complement graph, but somehow we are to update things accordingly. Maybe. Yeah, let's try something else. Let's take two components in graph 1. Now, for these two components in graph 1, we want to see if there's any maybe we can do this in n square root n if we play our cards right. Maybe n square root n log n, but I don't like that complexity. So let's see. I don't actually, that has no basis. Don't listen to me. That was a random thing. GCD. Cool. So consider two components in the first graph. If any two of these nodes are different components in the second, so by our guess in D1, we showed that it doesn't matter the order you add the edges in, and if you can take an edge, it's beneficial to take it, no matter what. So greedy is okay, at least in those test cases. Hopefully that doesn't bite me in the back later. But so if we consider two different components in the first graph, then we just need to see, are there any two nodes that are in different components in the second graph? And if so, we merge those two nodes, we merge the components together, everything is happy. And if not, if all the nodes of those two components in the first graph are the same in the second graph, then are like the same component, not the same node, of course. Is it safe to say those two components will never be merged? I believe it is. Because how would they be merged? Then you would need an edge to one of those components and to another of those components. So like what I'm thinking is, red is first graph, blue is second. So you have two components here, and there's this big component in the second graph that contains both of these red components, like all the nodes in them. Then how would you ever merge the red components? Because suppose you do somehow, like this, then you're merging the blue component to itself, because all these edges are also in the blue graph. That can't be possible. So those two components are forever disconnected. So does it mean we can treat them as merged anyway? Is that how that works? Yeah, I think it is. Because no matter what, there will be an edge. No matter what we do, there will not be an edge to both of these components. Because if there is, then like we're gonna have problems with this blue one. So we might as well merge these two components together. And that's the trick. Alright. I'm gonna go to the bathroom and then think about implementation for that. So I'll be right back. Probably mute the mic. We good? Hope so. Okay, so here's how this is going to work. We're going to consider all the components in order in the first graph. We're going to say this component is like the one we're looking at. So we say, can we stick on this component? And so basically we're going to put all of the part 2 components into like a multiset, and then like a map, I guess, with like counts or something. Sure. And then if any of these things have different components, then we save that pair, we add that edge, then we merge the 2 components. And then when we merge the 2 components, it affects some stuff in the second graph. So we update that with the DSU. And then we continue on. I guess that's the plan. Yeah. Let's just do that. Okay, so we're only gonna have one DSU this time. So for we're going to treat the first forest like a normal graph. D dot init n. So DSU is going to represent the second graph. D dot merge x y. Good. So now we create edges. All right. So basically I'm going to aggregate the entire component into a vector. Then, yeah, this b is equal to 1. Good idea. So if we have a new component, count v plus equals d. Count dot erase b. Okay. So essentially, this map is going to store everything in our current aggregate component. It's going to store the list of DSU components. So every node in the first graph is going to be characterized by its component in the second graph. When we do DSU, we update it manually and we change the components we change the component value of the smaller component, and by small to large, it'll be like fine. Actually, it might have time limit issues. So I will look more into that later. How much? Oh, that was fine. Okay. This might have time limit issues. I'm not really sure. That would be a pain if it did. Yeah, that would be a pain. We'll see. If we need to update it, we'll update it. By FST, whatever. I guess I have to do 2, doesn't matter. So we have extra time here, right? Yeah, we have extra time. Okay, so if not visited I. So cur.clear, DFS I. for each vertex in cur, if d dot marks x, if t dot first is equal to -1, so we still haven't found a match for each thing in the map. It's okay to iterate over this because it'll like, the complexity will work out, I think. Unless map iteration is stupid like it was before, which did happen before. I got totally screwed by map iteration, but there's no hacking phase on this contest, and I can't hack myself, so hopefully we'll be fine. And like it doesn't go over that many elements anyway. So for, yeah, there's definitely a way we can get rid of map iteration. I just I'm lazy. Count t dot f. No. So if y dot first is not equal to the component of this, then we have a pair. So t is equal to oh, that's a pain. Okay. That's definitely a TLE. Val dot insert b. So ints node, this should be del, then this should be insert. Again, there's a better way to do this if we have time limit issues, but I hope not. There's a decent chance we could fail system tests, but that's fine. I'm lazy. Let's iterate over it like iterators. Y first. T is equal to x. Y second dot begin. Okay, make sure we pointed the right thing. Break. Then ints at vx. Yes. If t dot f is not equal to -1. They love making us restore the answer, huh? They just couldn't let us be. Nope. Nope. Okay. T dot f is not equal to -1. Then d dot merge t dot f t dot s and stop push back t dot f t dot s. What? Come on. What does it think it is? Oh, wait. That's fine. Okay. I doubt it'll do anything, but 2. I mean, does this get 8? Does it? Is that the right answer? Can't tell. Why does it get 2 here? What exactly is it adding? It's adding 2, 1, which already exists, and 5, 1. Oh, wait, okay. That's why. That makes sense. Why? Just change that. What is the problem? What is the problem? I'm printing. How is this happening? There's nothing in count. There's nothing in count. Count is nothing. What is in count? Oh, okay. I did not do that at the beginning, that's why. Okay. If opt, do that. 0. And here we do 1. Okay, that will explain stuff. 3, 2 is fine. See how this works. Okay, so edges. Merge. Cur.clear DFS. For each thing in cur, if anything's different in count, then set those together. Then for each of those, yeah. B is d.marks x. Yep, then insert that. Then if t.f, if we have a pair, merge them, push them into the answer. So now the question is merge, so we do the standard DSU stuff. This isn't actually necessary, but it's fine. And then the hard is in mark, where every time we change something, we remove it from its current mark, and then we remark it. Ow. Okay, I doubt it will pass within the time limit, but we can try. Cannot hurt to try. Actually, it can. It'll give us penalty, but it cannot hurt to try. Was it wrong answer or TLE? Awesome, love that. 2 seconds, log squared is dying. Okay. So can we just eliminate the log squared altogether? The answer is yes. But do we have to? No, yeah, wait, this is fine actually. Because when a component's erased, it will always be erased like... Okay, that's fine. So we make this up to this. And the problem is, yeah. This is freaking annoying. So even then, deletions is like fine. Okay, so instead of doing this in mark, we'll get rid of that. Yeah. So push back V. And that should be at plus count val. You can use special properties of the problem. So when some component is removed, it is removed entirely, which means that we can get rid of everything. We don't have to do like erasures. So, all right. So for LLX at marks A at marks B dot push back X count marks B plus equals count marks A count marks A equals 0 and can dot erase marks A. We don't need this. Yeah, we do. Clearing isn't strictly necessary, nor is getting rid of the A stuff, but I'm doing it to be safe. So if opt, that's also important. So then canned, if y is not equal to v, then at y dot begin. That should work. But the idea is seemingly solidified. Come on. What? What's the problem? Okay, wait. Oh. Oh. Okay, that's one fix. The other fix is like this thing. What's the problem? X at wide up again. What is the problem with at wide up again? Pair? What? No. What the hell? How do you parse this? Should I do like 0? It shouldn't make a difference. Oh, maybe. I thought this didn't have... Oh, wait, it's back, not begin. Okay, I'm dumb. That was stupid. Yeah. Yeah, that's an iterator. Of course, that doesn't make sense. I was thinking like dot back, because that does return the value, but... Fine. So now nothing works, so that's awesome. And the reason is if count val is equal to 0, cand.insert val. Good. Otherwise, there are no candidates, so no colors will ever be used, and the whole thing is dumb. Makes sense. Same answer, I think. Same answer. Take 2. Looks like the queue is settled, which is nice. Pretest 11. Alright, looks like we got it. That leaves E. Mocha n stars. There are n stars which can be seen, and the brightness of the ith star is AI. Okay. This is probably not something I'm going to solve in 40 minutes because it looks mathy, but we'll see. N stars form a constellation, the state is an array. State is called mathematical. If everything is in a range, the sum is less than m is up to 10 to the 5th, and the GCD is 1. Okay. Cool. So the obvious dp and nm squared with some log is not going to work. So what can we do better? How do you do this without the GCD condition? Actually, no, it's even more states. I don't know what I'm thinking. Without the GCD condition, how does it work? Then it's prefix sums, and that's fine. Problem is that is not how that works. Because we do have the GCD condition. But again, without the GCD condition, we could do prefix sums, everything would be jolly. GCD could maybe be a lot of things, but also might not. Can't have the GCD as the state. But what can we have it as? Like n is small, that's a factor. Oh, each thing has its own. Okay. That changes things a bit. Makes it slightly harder, but I guess, I don't know. Sum of AI is less than M. So sum matters and the GCD matters. I feel like it's not DP, but who knows? Sum of AI is less than M. It is up to 10 to the 5th, so that matters. It's not some annoying math stuff, but it could be some annoying math stuff. I hope it's not. By the way, is things still working? Seems good. So it's us and this problem. This is the final stretch. What we gotta do. Range of the brightness of the star. May we consider counting it for everything that's not 1? I guess it could be like that. If we consider counting it for everything that's not 1, maybe that could work? If we could do it efficiently, actually. So we consider doing the GCD being the multiple of 1. And then, what if the GCD is specifically a multiple of 2? Then a multiple of 3, and so on. And that will theoretically work in O of something. Yeah, I can see that working. Okay, let's see. So essentially we're going to compute, I'm gonna have to be brief on the explanations here because we're kind of low on time. So essentially we're gonna compute like the naive NMDP. So without the GCD condition again, we can compute it in O of NM, which is fine, because that's fine. But what about the GCD condition? Then what we can do is we can say, well, what if the GCD is going to be a multiple of like 1? And that's fine. But then we need to get rid of everything that isn't 1. So how many ways are there to have the GCD, for example, be a multiple of 2 and a multiple of 3 and so on? Okay. Time to code. Let's do this. I'll explain this more in the solution. I gotta go though. Gotta be quick. Okay. So for li equals 1 as a signal n, f is plus. Okay. Three, 5, 3. Yep. That would be the answer. So now we need to compute. So it's not n, it's m. So that's a mistake. So for CB j is equal to 29. K is equal to I. K is also equal to m. K plus equals I. This can be sped up, I'm just being lazy. Dot first, j dot second, cvj dot first equals k, cvj dot second is equal to k. If worst is like greater than 128, f of I is equal to 0. Else, ask. So what should this be? M over I. J is 0, j is less than n, j plus plus. CVJ. Okay. Small, CVJ of second is large. If there's no value, then this will be invalid. Yes, okay. This part's not bad. So LDP 55 4 okay. So between Li and Ri. So if j is greater than or equal to cv I dot first, that's equal to r plus dp j minus cv I dot first mod mod. Yeah. dp I plus 1 j is equal to r. If j is greater than or equal to cv I dot second, now we lose that. R minus equals dp. So much trouble with this. I j minus cv I dot second. If r is less than 0, r plus equals mod. And it's plus equals dp n j. Good. Let's try it. Could still be wrong here. Max dot first. Could still be wrong here. There's a decent chance. 0. Awesome. Oh, f5 is equal to, yep. 4. 251. Alright, that was actually easier than I thought. I think it should pass the time limit. If not, I'll do some optimizations. But it's m log m times n, which I think is fine because n is pretty small. Yeah, there we go. Alright, contest over. So this is like fairly cool. Seems like it was a relatively easy contest. Yeah, people did E faster than D2. So it may have been a good idea to look at the dashboard in this one, because E was easier, but whatever. Yeah, I kind of expected it to be harder, but considering that this was worth double this, that is surprising, but I guess we're fine. Looks like second thread also registered late. That's pretty funny. Yeah, this penalty was horrendous. How do people do? Interesting. Congrats to Neil again. Seems to be very good at this stuff. And some of my friends are having very strong performances. Even having one less problem but having more points. That's what this atrocious penalty is doing to me. Yeah. Okay, that's over. Yeah, E definitely felt easier than D2. D2 is kind of like a thing. It's kind of hard to like. Codeforces is, I think it's like really annoying because it forces you to sort these alphabetically, and that means it forces these subtasks to be together. So even though D2 is definitely harder, generally harder than E, and like people are probably, it's probably like the general consensus that D2 is harder than E, and the setters probably knew this, but because D1 and D2 have to be together, and D1 is much, much easier than E, since it's sort of just brute force, make a guess, you're done. D is before E. So, like, this much harder problem is before this much easier problem. And this much harder problem is worth fewer points than the much easier problem. This is worth 1,500. You can guess this, and it barely gives you an idea for this. There's a much harder idea for D2. So it's kind of just weird how that works. Because E really should not be worth twice as much as D2. I don't know. That's what I have to say about that. And I think D should give me more points. I'm not really sure if the setters anticipated E to be much, like, at least 3 times as easy, because a lot of people are getting that. Well, this is kind of like standard. Like this GCD like subtraction thing is a lot. It's used a lot. Is the thing. There are a lot of problems that are centered around this trick. So that's the reason people recognize it so fast. Like, it's hard to come up with the first time, for sure. Like, if you've never seen that trick before, which I will explain in the solutions part, if you've never seen the trick before, then it's understandable to not come up with it. I probably wouldn't myself. But because it's shown up a lot before, like, it's sort of standard. And it's possible to recognize it. And then when you get that trick, then it's just write code for DP and you're done. Okay. So now I'm gonna have to go through the ordeal of explaining this stuff, although I have already partially explained this stuff throughout the screencast, so that's nice. Yeah, this melody is so funny. There are 3 people above me who just solved E faster and they got more points. That's so funny. Yeah. It's surprising that there's some IGMs that have been struggling. Yeah, seems like it. I don't understand what happened with B either. I still don't understand what happened here. Did I change anything within this? RP is 0, RP is less than RP plus plus. I'm gonna want to look at that later. I'm hoping it was just some implementation error. Interesting. We had the same score and the same penalty in the same time. I'm hoping it was an implementation error. So my rank is gonna slowly drop as this goes on. But like, I don't know. I don't really know what happened with that. It's kind of weird. What's gonna happen to these ratings? It's pretty good. It's master. Nice. Hopefully some other people will be not me and look at the dashboard and go for E. Okay. I'm gonna get a headache if I keep going like this. So let's just get through these solutions and be done. Now, I guess overall, like, I'll give my opinion on the problems. I don't know. Do you guys like that? I don't know if I like doing it. I mean, admittedly, I've been enjoying this stuff less, so my opinion on problems is gonna get more and more negative. But that's how it is. What is that? It's interesting. This like thing is frozen there. Can I freeze it? No, I think it jumps back. Okay. So this one was sort of like the operation is the disguise, but like it's also bitwise in problem A, which is not a nice formulation. Because if you don't understand that, then it's hard to like get the idea behind it. So I don't know. I feel like it's too much. But like if you get bitwise and, then this problem is easy. But if you don't have like intuitive understanding of it, and if it's like a new concept, then it's going to be hard probably. Like you have to understand like having a single zero will eliminate everything, and stuff like it's always going to decrease, and you always want to like and more, I guess. I don't know. Maybe it's easier than I make it out to be, but I feel like that may not be the best A problem. And this one, just like do it. It's like some stuff you'd find on a div 3. Don't like that one, especially because of this. But even without this, I would still not like it. So it's not that biased. This one was like, that's fine. I guess it was, personally I found it easier than B just because implementation was less, but it could still be hard. You have to like figure out the strategy, I guess. You have to figure out like, it's like sort of like proofs, like it's like a necessary thing to have this certain configuration, and then it's also, it's like necessary because there's no other way to do it, and sufficient because it works. That's sort of like the thing. I'm just talking about proofs. D1, I don't know. I don't think the subtask was necessary. I think if they didn't have the subtask, D2 could be after E, and then it would be worth more points, and then it'd be properly placed, because I think D2 is definitely harder. But yeah. I guess D1 is there to like prove your guess, kind of. It's kind of like a hint. Like you could possibly conjecture that it's okay to add any edge greedily, and then once you have like enough of an understanding to convince yourself, a lot of people will just go for the guess and not even think about it much, which is like fine, and it works often. And even if you get a penalty, it's fine. Sometimes it can lead to failing system tests, but not that often, because generally people have it covered. Like greedy is probably one of the first things you would think of when you come across this. So that is reasonable. Next part is, and then D2 is like a lot harder. Involves maybe a clever observation. I'm not sure if the thing I figured out was necessary, but that is what I did for it. It worked. It was a pain. Had TLE just because of like some stuff that happened. Yeah. But I guess if you get the greedy idea, then like I guess you're fine with this. It's just figuring out that observation. I don't know what I'm saying anymore. And then this was standard. Oh yeah. Let's just do this already. Problem A, solution. Right. So as I mentioned before, we're going to consider some properties of bitwise AND. In particular, bitwise AND is bitwise. It goes bit by bit, and it applies the AND operation to each pair of bits independently, which means that all bits are independent. So let's consider bits independently, and let's only consider a single bit. So assume that, like, for example, AI is between 0 and 1, so that it's only a single bit. And then we're going to do this for each bit independently. Let's consider, like, some cases. For example, all of these bits could be 1. Then the bitwise AND isn't going to change anything, because everything's 1 already. So 1 and 1 is going to be 1. But what if you have like some zeros? We want the maximum element to be as small as possible. So we want to get rid of these ones if we can, because that will decrease the elements. And it's always okay to decrease an element, because bitwise AND can only decrease. It can never increase. So what can we do? If we use the operation and we pick 2 elements, like if we pick L equals this and R equals this, then these two will become the bitwise AND of each other, and 0 and 1 is 0, which means this will be 0. So we do this again to every pair of adjacent elements, then everything can become 0. Note that this 0 didn't even matter. We only needed a single 0 to make this happen, because we can have this 0 like spread out everywhere else. Like this can spread out this way, and it can spread out this way. And some other zeros, like if we had a 1 on this side, this 0 could spread out. So if we have a single 0, then we can have a 0 everywhere in this bit. That's the basic idea. So otherwise, the bit is going to be 1. So what this means is that all of the final numbers are going to be the same in the optimal solution. Either 0 if there's at least one 0 in this bit, or 1 otherwise. So we can go through and we can count the number of 1s in each bit position, and we can say it's going to become 1 if that, and otherwise 0. But there's a different way to think about it, that having at least one 0 means 0, and otherwise 1, is exactly the definition of bitwise AND, which is sort of convenient. So really it turns out that the answer is the bitwise AND of the whole array, because each bit undergoes like the logic that bitwise AND would have you take. If you have at least one 0, then you will return 0 for that bit, which is what bitwise AND is. And if you have all 1s, then you have a 1, which is what bitwise AND is. So that's one way to think about it. So really the solution is just the bitwise AND of the whole array. Another way to think about it is like, because you can do adjacent elements, you can sort of just like AND every pair of elements together. And then if you do enough ANDs, if you do enough operations, like everything will eventually be ANDed together. So sort of intuitively, like the answer ends up the same. It's the bitwise AND of the whole array. So there are multiple ways to arrive at this answer. But essentially, that's how it works. You can start the bitwise AND with the first element and then AND it with everything else. Another way to do it is to have some like huge element, like some element that's all 1s in binary. So like 2 to the 30th minus 1 or something. And then that will work too, because 2 to the 30th is greater than 10 to the 9th by a bit, so that would work. Pun not intended there. Yeah. This problem, that was fun. I don't understand. Yeah, there's something with this problem. Something happened with the code here. Something happened. I don't know what happened, but something did happen. I still don't understand what happened. Let me actually compare these. So what is the difference here? So this is the only difference. I got rid of this part. And something happened here. And somehow it worked. So okay, I'm going to present the solution that worked and ignore the part that didn't work, I guess. So basically we have this string, and we want to figure out like how do we minimize this value. Right, so what do we got to do here? So first, let's think about the endpoints, because they're kind of like special cases. So for the endpoints, what we can do is we can basically say like, this should not be equal to this. So let's make this the opposite. Then say we have another question mark like on the end of here. This should not be equal to this, so this should be the opposite of this one. So then this should not be equal to this, so it should be opposite, and etc. So basically it's going to alternate like that. So same on this end, this should be B, this should be R. So it's going to alternate. That's what the string is going to look like at the endpoints. But what about like in the middle? So there are two possible cases. Suppose we start alternating from here, and then it just like, everything just works out. Like, so this is going to be R, this is going to be B, and then we get through this with no penalty. Then everything's perfect, because we have 0 additional like costs to the string. So that's good. But what about the other case where we are forced to have some cost if we alternate. Then the idea is no matter what, we're always going to have some cost. So we might as well alternate it in like any possible way. In particular, like what am I saying? In particular, like we can alternate it like something. Like we can alternate it based on this one element. And then this will become the opposite of R, and then this will become the opposite of B. And then this will have exactly one cost. And is there a way we can do it without one cost? The answer is no. Because this has to alternate, this has to alternate, and this has to alternate. But if we do this, then no matter what, something's not going to work out. So we have to pick one point that's not going to alternate, and then everything else would work out. Yeah. If we do it like this, for example, then that point wouldn't alternate, so we'd have a cost. But if, for us to have a cost of 0, everything would have to be different. And we just showed that's not possible. Because if we try to do that, it's not going to work. In any possible way that we try to do it, it's not going to work. So there's no way we can do it, and therefore we have to have at least a cost of 1. So to get a cost of exactly 1, we can just start alternating from one point and make it so the only point that's like causes the cost is one of the endpoints. There are other ways to implement it, I'm sure, but this felt easiest to me. I don't know. That's felt easy, and then it wasn't easy. But that's the basic idea. Like, so essentially you can pick an endpoint and start greedily alternating from that, and it works. As for the case where there are all question marks, you can just like, you can either handle that separately or like handle it smartly. But of course, you can do whatever you want with that string as long as it alternates. Code is here. It's sort of like 2 pointers like. I describe how the 2 pointers works like in the screencast. Basically, it's like we have a left pointer that's going to point to the current question mark. And then the right pointer is going to point to like the current index we're at. Then if this index is not a question mark and the left is before us, then that means we have this group of question marks that we need to process, and these are the endpoints. Specifically, L-1 to R are the endpoints. And then when we do this, we know this is not a question mark, so we set the next question mark to one ahead of this, L+1. So now we move R over here. This is a question mark, so we do nothing, because maybe we have more question marks to this side. So now we move R again. This is a question mark, so we do nothing. This is not a question mark, so we know this should not be L+1. Sorry, it should be R+1, but this is just L over here. Now we know again that the interval is from L inclusive to R exclusive. Now, so this is an interval of question marks, so these are the endpoints. Then we continue on. We move L to 1 past R, we move R forward, we move R forward, we move R forward. We have this group. We move L forward, move R forward, move R forward. And now we're at the end. And because L is not at the end as well, then we have this group here. If there was like a B here or something, then we would process this group, and then we get rid of this. And then because we have a B here, we would move L past the string, and so this group wouldn't exist. And so that's how we check like if there's something at the end. Code-wise, this is what's happening. And then I start the alternation. I start like the alternating stuff like based on the right point. Because when we're inside the loop, we know we're not at the end. And if we're not at the end, then we always have some right frame of reference, like to the right of the current group. So we alternate based on that. And then now this last part is the special case for like at the end, in which case either we have a left frame of reference or the whole string is question marks, in which case we can use any frame of reference. Like we can just pretend there's a B here. But maybe there is a left frame of reference, in which case we alternate based on that. And so stuff is happening there. I kind of want to, like, in case I'm misleading you though, I kind of want to figure this out. Let me just test this a bit more. So 2, 5, 5. Okay, I mean 2, 5, 5. BRBRB, BRBRR. 4, 5. What the? 4, 5. 5, 5. Which one of these does it get wrong? Does it get any of them wrong? Doesn't get that one wrong, doesn't get that one wrong, doesn't get that one wrong, doesn't get that one wrong. I really don't understand what happened here. Like, something happened in this code that was wrong. Because this was a problem. The problem was if LP is not equal to 0, then do stuff here. One, 7. It. Okay. Must just be some stupid bug. Stupid typo or something. I'm genuinely so confused on what's happening here. Could it be like... Maybe it's this. Maybe that's the problem. Could this be the problem? Wait. That could be it. That's it. Okay. Oh my god. So it was this. Because RP is exclusive, so this condition is actually fine. Okay. Alright, so everything I said here was correct. So it was just a bug in implementation, as I expected, but whatever. Okay. So that leaves a few other things. This problem was a bit interesting. Essentially, we have a directed graph. We have first nodes 1 to n, and then we have a special node n plus 1. I'm writing the numbers here because otherwise I'm going to say the wrong things. So I apologize in advance if I say n for this node instead of n plus 1. But essentially, we have a graph that looks like this. First, we have edges from node 1 to 2, node 2 to 3, node 3 to 4, node 4 to 5, etc., up to n. A node from I to I plus 1, essentially. And then we also, every orange node has an edge with a purple node. And depending on this given sequence of 0s and 1s, either the edge goes from orange to purple or from purple to orange. It can be either way, and each node can be different. So for example, I could have something like this. The goal is to find a path that starts somewhere, ends anywhere, ends anywhere, and visits all nodes exactly once. Essentially a Hamiltonian path, if you're familiar with that description. Actually, I think that's right. I don't know. I think it's a Hamiltonian path. But the question, and we need to print the path, of course, because we always have to restore the answer, and it wouldn't make sense otherwise. And we also print -1 if it's impossible, but it's actually never impossible, so that's fine. So let's start with some like easy strategies. Which node do we start at? That's the first question. So what if we start at n plus 1? then we're never visiting n plus 1 again. So once we go to orange, we're staying on orange. So we need to pick some orange node so that from this node, we can visit all the other orange nodes, right? There's only one node that can do that, and it's node 1. Because everything else, nothing else can get to 1, because we can't go backwards, because all the purple edges are gone. So we can start at n plus 1 only if what the hell? We can start at n plus 1 only if we have this edge. So if we have an edge from n plus 1 to 1. If that's true, immediately we're done. Otherwise, now we assume that this edge goes this way. Let's consider a different strategy. What if we start at 1? Well, what if we just take the easy route and go from 1 to 5 and just do all the orange ones first? Then that only works if we have the edge from 5 to n plus 1, or n to n plus 1. So that's another strategy we can use. And otherwise, this edge has to go this way for that to not be possible. So now we have this edge has to happen, otherwise we have an easy strategy, and this edge as well. So now the question is, what do we have left to do? We already noted that because this edge goes this way, we cannot start at n plus 1, otherwise there's no way to finish all the orange nodes. So we have to start somewhere in orange. And if we start anywhere other than 1, we can never get back to 1, because again, there is no edge going into 1. So we can never get back to 1, so we have to do an orange node. Right. So now when do we visit n plus 1 is the real question. And is my mic working is another question. Sounds like it. Yep. So now that we've answered the second one, let's answer the first one. When do we visit n plus 1? So we're going to start at 1, and we're going to take a peaceful stroll up until some node. Let's say it's 2, for example. It doesn't have to be 2, but let's just say it is. Then from 2, we're going to go to n plus 1. Then where can we come back? Well, again, we have to visit the rest of the orange nodes, and we can no longer consider n plus 1 because we've already visited it. So we need a node that can reach the rest of the orange nodes, and the only node that does that is 3. So the only other possibility is really that we go from some node to n plus 1, and then we go right back to the node that's right after it. And the only way that's possible is if we have some adjacent pair of edges like this, that this will go out to n plus 1 and this will come back from it. If this exists, then we can use this strategy. But remember, there's a reason I had us consider the simple strategies first, because this edge has to go this way, otherwise we have the easy strategy of starting at n plus 1 then going to 1. This edge has to go this way, or we have the easy strategy of starting from 1 and then just going to n plus 1 at the very end. So, because both of these easy strategies aren't possible, these edges go this way. So there has to be some point where this goes out and this goes in. This goes out and the next one goes in. Because let's consider if there isn't a point. Then this one has to go out, because if it went in, then this would happen. And we're trying to make that not happen. So this one has to go out, and this one has to go out, and this one has to go out, and this one has to go out, but wait, it can't, because we already said this one's going this way. So we have this, and we can do it. And if we have this any earlier, then of course we can do it then. So, proof by contradiction, essentially this has to be possible. So we're looking for some configuration that looks like this. If we can find that, that gives us our answer. But what about the special cases? They're kind of annoying, right? Well, as it turns out, we can sort of factor them into the solution. Because consider when it's possible to do a special case. In this case, we would have this edge going in here. We would start at n+1 and then take this edge along. That's a horrible edge. We would take this edge along. But it's kind of like we already have half of this, and then this part is just like over here. It's not actually on the grid. And the same thing kind of goes here, that like over here, if we have this, then we have the easy strategy of starting at 1, then going here and being done. So again, it's kind of like we have half of this, and then the other half is just off the map. So really, like, implementation wise, it works to sort of just stick an auxiliary like this edge here, and then an auxiliary this edge, and then we can simply check for each pair, for each adjacent pair, like including these, do we have this configuration? And then if so, then this is where we put n+1 in the sequence. If we have the configuration, for example, here, then we would print the sequence 1 to n as part of the answer. Now I'm showing how to construct the answer. And then in between these like two arrows that we have, we stick in n+1. So suppose we have the sequence like here, for example. Then between 3 and 4, this is where we visit 6. So we sort of take a detour to 6 and then come back. So really we stick the 6 in between 3 and 4. So just finding the position of these arrows tells us exactly where we should put n+1 in. Because really that's what the sequence is going to look like. It's going to be the sequence 1 to n, except we stick in n+1 somewhere. This is a 5. Yeah. So that's the whole plan. This visual may help too. It's essentially like we just detour to n+1 and then go back along our original route. So yeah, implementation wise, you could potentially stick an additional 0 on the beginning and an additional 1 on the end, and that would make implementation easy. There are other ways to do it too. I just simply said, like, if we're at the right index, then we only check one thing. If we're at the left index, then we only check one thing. That's essential. Or yeah, other way around, like visually. Like this is left, this is right. And I can't even load my code because system testing. But that's how the implementation will work. Then at the appropriate position, you would print n+1. Okay, I'm going to let that load. Alright, so reading the array, then if we're at the left and either we're at the left or we have a 0 on the left, or we're at the right, or like and we're at the right or we have a 1 on the right, then it works, and then we print n+1 and then we make sure we don't print it multiple times. That could happen, maybe you do print it multiple times, so make sure you don't do that. Yeah. And then it'll print the sequence like that, it'll just stick the 4 in somewhere. Problem D1. I feel like this is one of those problems where they like there was some A and some like, I think it was the last div too, basically. It was like, they had like a simple, it was like a simple solution, but the proof was like monster. And the editorial proof, even that was incomplete. Like there were some cases they didn't cover. There was some comment that did it elegantly, but like the editorial proof wasn't enough for the A. So it's like, it's really annoying for, I guess for me, because I have to explain stuff and I try to prove everything. And so going through that A and like having the proof be way harder than the problem is really annoying. A lot of times they're basically just asking you to guess. Because there were like, I don't know, like 5,000 solves, 4,000 solves on this. I doubt that many people could really like strictly like prove this to be correct. I'm guessing a maybe not a majority, but like a decent portion at least just guessed that you could do greedy and it'd be fine. Maybe it was probably intuition, probably, I don't know. Maybe it's like simpler than I thought and it's like related to some like spanning tree stuff. It could be just extendable to a spanning tree proof, but I still doubt that everyone proved it. I don't think that's how Codeforces works. So beyond my rant, let's like actually talk about the problem. Thank you very much. The basic idea is that if we can add some edge, we should, which is greedy. So we can greedily add any edge that will be valid, which means it will merge components in both forests and it will be separate in both forests. So also to note that like if we add an edge, it's going to merge two components, because if we cannot add an edge, then it was in the same component in at least one of the forests. But we can add the edge, so it's in different components in both forests, and this edge will merge the respective components in the forests. So each edge will merge a component, meaning like there are a limited number of edges, at most n, which is necessary for this one because we have to print the edges. I don't even like guarantee that H is printable, but I guess it's fine. If you saw, or I guess with some DSU ideas or like spanning tree stuff, you can like fairly easily conclude that there are not that many. There are like a linear amount of edges you can add. So essentially, greedy. The proof is sort of like, I don't know. Like I don't know how to prove it, but the basic idea is like if you have an edge that you take, and then like maybe that edge is bad, but the edge is only bad if it prevents you from getting like more than one edge in the future. But I guess like relying on intuition here, if one edge prevents you from getting more than one edge in the future, like how? Because one edge can merge two components. So if multiple edges, like multiple edges that are compatible with each other, are barred by merging a single pair of components in each forest, like that doesn't make sense. Because those two edges that you would take would merge two different components. Which means that like suppose like you have something like this. Then maybe taking these two edges relies on this, right? But both of them can't merge these components together. This can't be the case, because then those two edges wouldn't be compatible with each other. So at most, one of these edges can merge these components together, and the other has to do something else. Even when you consider both forests, like this is the case, sort of independently. And there is the possibility that one edge will like, maybe there's an edge that works in one forest and an edge that works in another forest, and taking the edge you take blocks both of these. But like, because every edge is possible, like there's not a restricted set of edges you can add. You can always add like every possible edge. Then this would work. If you had a restricted set of edges that you could like add, then greedy would not work. Just to make that clear, because there was a case that if you restricted the edges, it would break. But because you have every edge possible, I think that also contributes to why the answer is possible. But here, like, this merges these two, and then... So if you took this edge instead, then you would only need to get rid of one of these. This edge would still be fine. So we're like, it's okay to take that edge. So if you can convince yourself that greedy works, which I can't, but if you can, somehow, and then we basically just need to do the rest of the problem. Now, one thing you can do is note that we add at most n edges, because there are at most n-1 components. Each edge will reduce the number of components by 1, so there are at most n-2 edges that we can add. No, sorry. There are n components. Each edge will reduce 1, so there are at most n-1 components, edges that we can add, so that we'll have exactly one component left. The thing with that is that, like, what is the thing with that? So yeah, what that means is that, like, when we're looking for if two things are in the same component, when we add an edge, we can manually DFS and like refine the components in each forest independently, so that we can continue looking through edges. So like for D1, The point is we're going to brute force every pair of edges. We're going to look at each pair of edges ij, or maybe like AB. If it works in both components, if they're separate, then we add those edges in. So because n is 1000, we can manually re-DFS and refine components, and then that lets us check. Another simple way is using DSU. That lets you quickly maintain like what's happening in each forest. That's probably easier to implement, so that's what I did. Codeforces, thank you. Yeah. So I have 2 DSUs, 1 for each component. I specifically avoided using M1 just because like 1 is very similar to 2. So I only put 2 on one of them to prevent that mistake. It's not strictly necessary, but I did it for like myself because I've definitely made that mistake before, like using 1 and 2. So yeah. Probably a better idea to just use better variable names in the first place, but that is not who I am, so we'll stick with this. So read in edges for the first forest, read in for the second. Literally look at every pair of edges, check if they're in the same component. However your DSU works, generally you have like a find function. Mine is a bit different. Mine is like union by size, and it will manually relabel the nodes in the smaller component. So it's n log n, but yeah. Then if the edge works, push it to the answer, merge in both, and then print the edges. D2, so yeah, that's D1. It leaves D2. I don't even know why I drew this. It didn't like do anything. I don't know how to like draw visuals for this, but yeah, that leaves D2. So again, for D1, brute force edges, add edges that work. If an edge works, it's okay to add it because greedy. So D2 is going to rely on this greedy idea. Jeez. We have to do it more smartly. This was not smart. This was n log squared. It was technically correct complexity, but the time limit's ugly. So that did not work. So the basic idea is consider 2 components in the first graph. So we're going to do red is first, blue is second. Consider 2 components in the first graph. When can we merge these 2 components? It's possible if and only if, I guess, there are, if and only if, like there's a node here and a node here that are in different components in the second graph. So what I mean is like we can add an edge here. This is sort of like, this is obvious based on the definition of the problem, but you can only add an edge here if there are 2 different components, or if there's a node here and a node here that are in different components in the second graph. Because if all of the nodes are in the same component in the second graph, then there's no way to add an edge, because everything would add an edge from this component to itself, and that wouldn't work. So there have to be 2 different components among here, which we can check for fairly easily. But the problem is like, then what? We have these 2 components. So if they're in the same component, then we're sort of like left with no information. All we know is that these 2 components aren't compatible, which is a pain. But here comes the claim, and this claim sort of makes up the rest of the problem. If these 2 components can't be merged directly, then they'll never be merged. And actually, maybe that's not the biggest claim, but if these 2 components can't be merged directly, then how would they be merged indirectly? Because to merge them indirectly would require some sequence of edges that eventually results in these 2 being connected. But then, again, this sequence of edges would connect this component to itself somehow, because this is in the blue component and this is in the blue component. So that sequence of edges is impossible. So if two components can't be connected directly, they'll never be connected. That part actually is probably clear. But what it means is that implementation-wise, it's equivalent to having merged these components in the first place. Because it's like, with two merged components, we can never add an edge between these two components. Because like, you know, otherwise it would connect them. But we just discovered that we have that property anyway. No matter what, we can never add an edge that connects these two components. When we already connected them, it's because we can't merge the red components together. But here, it's because we know we can't merge the blue components together. So like, functionally, they're already merged. And that is the big idea. That no matter what, when we process two components, we can consider them together for the rest of their life. Because either we can merge them with an edge, in which case we do, or they're already merged in the other graph. And that means that these two are basically in the same component because they satisfy all the properties of like merging that a single component would satisfy. So functionally, they're merged together. And that's what I base my solution upon. Because now that this is merged together, we can treat this like one big component no matter what we do. And so now we process another component. And now we have this big red component and we do the same thing. We ask, can we merge them together? And if so, then we explicitly add an edge between them. And if not, then we functionally merge them together and we consider some new component. And we do the same thing. You know, and then the circles get bigger and bigger and I run out of space to draw. But that's what we're doing here. I hope that makes sense. Functionally, they're the same. The set of edges that can be added, like the set of edges that can be added to this pair of components is the same, regardless of whether we can merge them initially or not. I'm just repeating myself here. But yeah. So functionally, they're merged together. I don't know. Like, that's the main idea. And then from there, it's like, then the annoying part is like, or maybe it's not annoying. I don't know. I guess it's like the implementation-y part of the problem is that we have to efficiently ask, like, can we merge these two together? And efficiently is not in n log squared n, apparently. Or at least not n log squared n with a horrible constant. But the way I did this is, essentially here, I'm storing a set of the blue components that exist in the red, in like the current components. And for each component, you get a count of nodes, like the number of nodes in this red component that's in that specific blue component, and a list so that we can restore the answer. Restoring the answer is also part of the thing. So in particular, it's a set of blue components. Like, this is the possible blue components that are in the red component that we're considering. And we have a count and we have a list for each of them. Like a vector, whatever you want to use for a list. When we consider a red component, we consider each node individually. And we just need any possible pairing that can work so that we can restore the answer. So for example here, like, we consider each node. So for a node, we go through the set. If we find any pair of components that are different, like if this blue component is different from any of these, in particular, if there's more than one, we will find a difference because like this can't be equal to both of them, of course. And if there's equal one, then we might as well iterate through them because it's one iteration anyway. So like we just need to find a difference. If there's any difference here, querying the set, then we query the list. In fact, you don't really need the count. The list sort of makes up for it, but the count is just like functional. Actually, you don't need the count at all. I'm just gonna get rid of that, I think. I don't think I ever actually used the count, but it doesn't really matter. Yeah, so we consider each thing. Then when we find a match, we query the list, and that tells us the edge we add. If we never find a match, Like if we never find an edge we can add, then we conclude that the components cannot be merged together. We do not add an edge, but we still merge them together like functionally with respect to the blue components that are currently there. So when we merge a component, we add all the blue components here into here. Specifically, it's possible that like the set is still of size 1, there's only one blue component, and we also add everything to the list. So this is all fine and dandy, because we can just like, this is just adding it on. It's linear because the total number of nodes is linear. But the problem is, when we do this, when we merge components in like the red, we're also merging components in the blue. So some of this stuff will change, and some of this stuff will change. Now, how do we determine what changes? I think this is where my DSU implementation comes in handy. Because the way it works is, instead of like normally like storing parents, it will, when you merge two components together, it will manually recolor the smallest one. So like when I merge these together with an edge, it will find the smaller component, and it will manually like set all these nodes to be part of this component. And by some arguments, it's like n log n. I'm not gonna go that deep into that, but in total, it's like its complexity is fine. It's n log n. But that works because now, when we relabel a small component, we just move it from the old list to the new list, which could be annoying. But the convenient part is that when we remove a component, we remove the entire thing, which means we don't have to erase from a list. We just clear a list. We move the entire list to a new component, and we only have to erase one element from the set. We just remove this component in particular. So like the bookwork required isn't that bad because we get rid of whole components at once. So in particular, this indentation is messed up. But like when I get rid of a component, like for each thing in the old component, I will move it to the new components list. I will get rid of everything in the old component list, which doesn't actually matter memory-wise. I don't think. I think it uses the same amount of memory anyway. Clear doesn't actually like, I don't know. There's a possibility that clearing it doesn't actually get rid of the memory, though I'm not sure. And then I add to the count even though it's not used. And then I erase the old component from the set because it's no longer a blue component. It is now merged into the collective component. The bigger one. I was trying to make a joke there, but I forgot what the words were, so it didn't make sense. Yeah. In terms of other implementation, we can use like, I use DSU for the blue components, and I just use DFS for the red ones. Like you go through each red component, you find the list of nodes that are in it, and then you like merge them manually. So here, I use like an edges list. This is DFS. I just collect all of the nodes of a single component and then set them to visited so I don't revisit components. Then for the second one, I merge them. For the first one, I push them to an edges list. For each node, if it has not been visited, then collect everything in its component. This is the possible edge that we'll add. It's like the match, like the edge that would merge two components. So we look at each node in this component, like the new component, the new red component. If anything in the candidate list is different, then we find our match. We're good. It's okay that it goes through the rest of this loop. It doesn't really matter. We just need like any match at all. Then for each thing, now we insert the values in this red component into like the collective red component, effectively like merging these together, whether with a red edge or with an edge that's part of the answer. And then merge if it's applicable, and like add to the answer. This merging is for the fact that we add this edge, so it becomes part of the second graph. I feel like that could have been confusing. In fact, it probably was at certain points, but hopefully the main idea was like understandable at least. I don't know. One can hope. System testing is not started. That is cool. Where am I still? Have I like dropped down even further? I'd imagine. Yeah. Nice. Penalty is very funny though. Still, the people with 5 problems could beat me. It's because this is so bad. I think, yeah, definitely going for E first was the move. Probably even like before B in my case. Maybe before D1. Because that was 16 minutes, that was 22, and that was 34. But whatever. This last problem was arguably probably easier than D2. At least it was much more standard. D2 had like an original idea, so I think it was cool. Maybe it wasn't original, but like original for me. So that was cool. In this one, we're going to use a trick that like has come up before. Essentially, we're going to ask, how many sequences have GCD be a multiple of 1? And the only way we can do that is we're only using multiples of 1, like we're only considering them for the sequence. Then what about 2? Then it means we can only use even numbers in the sequence. So essentially we're like compressing the sequence and we're only considering even numbers. So what if it's a multiple of 3? Then we do the same thing. We only use numbers that are divisible by 3 and so on. And we're going to do this up until n. We want to compute for each like number, or up to m, the number of sequences where the GCD is a multiple of that number. So in particular, to do this like transformation from the problem to having any numbers to having it be a multiple of a specific number. If it's a multiple of x, then like the numbers within an interval have to be multiples of x as well. So suppose like x is like 5 and we have the interval like 11 to 27. The numbers that work are 15, 20, and 25. So really the interval is 15 to 25. And then m, like the value m, must also drop down to like floor of m over x. And then this will be divided by 5. So this is like 3 to 5. This way, like, we process it in O of m over x instead of O of m, which is important. Now I have hiccups. What the hell? So essentially, first we're for each like value, we're finding the ranges that work. Luckily, n is at most 50, which is important. So find the ranges that work. You can do this like naively, which I did, or you can do some math to figure out the numbers, like ceiling division, for example, and stuff like that. Like this would go up to the nearest multiple of 5, and this would go down to the nearest multiple of 5, so you can do some stuff to figure that out. But if you process it naively, it's also O of m over x because you only iterate over multiples of x. And then, so the way we solve it like this is now we can ignore the GCD condition because we already said the GCD is going to be the multiple of x, i.e. multiple of x. So m will become m over x. Because like we're shifting the entire thing down by x. Like we're dividing everything by 5. And so the reason we floor is because if m is like 32, then like we can only go up to 30, so we might as well floor it and then we can go down to 6. Because like having 6.4 is pointless. We can only go up to 6. Scaled down by 5. I don't know if what I'm saying makes sense, but like basically we're going to divide everything by x so that we can process it in O of m over x. Like basically we have a reduced subproblem where the problem is only m over x. So how do we, now we just need to find the number of sequences where every number is an integer in the range li, ri, given, and the sum is less than some given number. This can be done using dp. In particular, dp of I, j is sum, like the number of ways to have a sequence with the sum of j after first I numbers. And the answer is the sum from j is equal to 0 to m of dp of I and j. No, dp of n and j. In particular, like this reduced m, like m over x. So now we're considering only the reduced problem. So we set m equal to m over x. We replace all the like intervals with the reduced intervals that only consider multiples of x. And we're solving this problem. Now, how do we transition? Well, this number can be anything from Li to Ri. So the previous sum can be anything from j minus Li to j minus Ri. So it's the sum from j is equal to L of I to R of I, index how you will. Like, I use 0 indexing, so it works. Actually, it doesn't work out. Maybe 1 index? I don't know. It doesn't matter that much. As long as you like process each interval smartly. I don't know. This actually uses 1 indexing, but like, yeah, it should be fairly clear anyway. So it's the sum from, no, this shouldn't be j. This should be like k or something, some other variable. Essentially, the previous number can be anything from Li to Ri, so the previous sum has to be, like when we add a number from Li to Ri, it has to become j. So the previous sum has to be between Li and Ri below j, and anything works. So essentially, we're considering all the numbers that can be here, and because the total sum is j, this other sum must be j minus x, and x is between Li and Ri. I feel like I'm over-explaining this, but that's how we do the DP. This can be optimized with a prefix sum. So that's how you do it in, I guess, optimal complexity. I'm not really sure if it's optimal, but like that gives you a good enough complexity. So instead of O of m over x, this will be O of n. That's a big O. This will be O of n because we have n times m over x states, and each state transition is O of 1. So we have O of n times m over x complexity. So what is the total complexity of just figuring this out? I'll explain why we're doing this after we like work out how we do it, which I should have said earlier. But the sum of this complexity is sum from x equals 1 to m of n times m over x. We can factor n out. We can even factor m out. So it's nm times the sum from x equals 1 to m of 1 over x. This is the harmonic series. I will once again link my blog on this because I've done it so many times. But basically, this is O of log m. So in total, this is O of nm log m, which will pass. In fact, comfortably. My code is like 200 milliseconds. Or 300, which is fine. So this is how we do it. Now, why are we even doing this? I didn't explain that part. And the reason is, we're trying to find for each thing, instead of multiple, we want exactly. So suppose we have like, let's continue with 5. Suppose we have the value, let like f of I be this. It's the number of sequences with GCD multiple of I. And we want g of I is to be the number of sequences with GCD of exactly I. So what is, for example, g of 5? Well, all we know is f, so somehow it has to be related to f. But what can we subtract out? Well, we know it's a multiple of 5, but we don't want it to be a multiple of 5. We want it to be exactly 5. So what we do here is we subtract out all the multiples of 5 that aren't 5. So for example, we would subtract out 10, because 10 is a multiple of 5, so we need to get rid of it. But we still want 5. So if we know g of 10, and we know g of 15, and we know g of every greater value, then we can compute g of 5. ... Up until like g of m, maybe. Because m is the largest number we can have, so we can stop at m. So essentially, we're subtracting out all the multiples of that number that isn't the number itself. So how do we know that we have g of all the greater numbers? Well, we just iterate backwards. We process from m to 1. So we compute g of m first, then g of m minus 1, and then so on, up to g of 1. And g of 1 is the answer. It's the number of sequences with GCD exactly 1. So in fact, if they had wanted, they could have like asked us this for like every x, and we would be able to answer because we know these values g. But instead, the answer is just g of 1. It doesn't really matter because they have a strong enough sample that it's fine anyway. Like this is a nice sample. I'm glad they had that. In fact, yeah, they generally had strong samples throughout this contest. I did like that. I do like strong samples because it makes it like less annoying and stuff. But I get there's also value in like making you debug yourself, whatever. I don't know. It doesn't really matter at the end of the day, but eventually you have to learn those skills no matter what. But yeah, that's how we do this. This is also, so we're subtracting out all multiples, so maybe it's m squared. But once again, for each multiple, for each value x, there are O of m over x multiples. Specifically florid, I think? Doesn't matter. But there are m over x multiples, so it's once again the sum from x equals 1 to m of m over x, which again is m log m. So the total complexity is dominated by this, the computing the dp stuff. So the total complexity is nm log m in total. Code-wise, this is exactly what I'm doing. So first, read in stuff, read in the intervals. Then to find the intervals that correspond to only multiples of x, I'm just doing it naively, literally. Like, do it naively. Then if nothing works for a particular interval, then f of x, or like I, has to be 0 because there's no way the GCD can be that. There are no multiples of that number for some interval, so it doesn't work. Otherwise, we divide everything by I. Note that this is flooring, that's by default. And then we compute the dp for that. So resetting the dp is essentially using prefix sums. We include the left if it's part of it, and then we exclude the right afterwards. So like it's sort of like maintaining a sliding window that contains the sum of j minus l to j minus r. Yeah, j minus r to j minus l, I guess. And this is like a running sum. It's not the r value. And the answer is exactly what I said in the thing. Like the answer is the sum over all values up to m of the dp, and then return that. I was also careful to not like overly use mod. If you explicitly use modding instead of like smart mod, then maybe it'll take longer. But smart mod is essentially like, you know that the value is at most like 1 mod away, so you can just subtract mod. If both of these values are less than or equal to mod, then it can't be greater than 2 times mod, and that means that it's only 1 mod away. So you can subtract the mod here, and you can add the mod here when you subtract, if necessary. Same thing here. We just subtract out all the multiples, and then the answer is f of 1. So yeah, that is how that goes. Hope for no system tests, but like could happen. I don't know. Maybe. So who knows? My score kind of makes it look like I started the contest late, but I just screwed up B, like initially. Yeah. Alright, I'm still glad I finished the contest, even though it was like very bad time. So that's how that went. Okay, I think that's enough of this. I don't have more to say. Overall, it was like a pretty cool contest. At least some of the problems were cool. Some of them weren't. but some of them were. Yeah, okay. Goodbye.